Hello everyone, this is Mr. G, and I'm going to work a couple of problems here involving Newton's laws of motion. Okay, so problem number one. Let's say you have a block suspended by a string. All right, so here we go. Here's a block. And there's a string attached to it. And that's being held up. And yeah, there's something up here holding this thing up, but I don't know what it is. And we're not too concerned about that, right? It could be attached to the ceiling, right, like that. It could be there is a person standing here, holding onto this thing, right? At this point, we're not too concerned about what's holding up the string here. So then let's do this. Let's say that this block has a mass of 2 kilograms. Okay, and we want to know everything there is to know about this block, all right? So initially, if it's just sitting there, it's not moving. So then we know a couple of things. We know that its velocity is 0. We also know its acceleration is 0. And so some questions that we might ask about this would be, for example, what is the weight of the block? Or what is the force of gravity on this block, right? Right? So, yeah, if this block is near the surface of the Earth, there is a force of gravity, gravitational force, acting on the block. That force is called the weight of the object. That's a force, and it's measured in newtons. And then we can represent that as a little arrow, a vector, right? So I'm going to draw a little vector here from the object's middle here. And the weight of an object is easily calculated. It's the mass of the object times little g. So, and in this case, that has a magnitude of 2 kilograms times 10 meters per second squared, about. So 20 newtons. Okay, there's a downward force on this block of 20 newtons, and that's the force of gravity. Okay, then what's the tension in the string? Right? Remember that for a string, right? If there's a force, if that string is exerting a force, we call it tension. That string is holding the block up. So there's an upward force acting on the block here, which I'll represent with another arrow and label that T for tension, okay? Now I know a lot of you are saying, well, this is ridiculous. Obviously, that tension is the same as the weight of the block, etc., etc. Why do I even have to draw this picture? It will become clear, hopefully, why we're drawing this little picture. All right. This picture, by the way, that shows the object and all the forces acting on it has a name. It is called a free body diagram. And it's going to be important that you're able to draw this free body diagram with these representations of force to solve problems. At this point, yeah, it's pretty clear maybe that the tension is equal to the weight of the block, but in other cases, it won't always be that clear. And this picture will really help you guide you towards whatever it is you're trying to solve for. Next, you need a coordinate system. Same thing as we've been doing since the beginning of the year, all right, when we talked about motion and kinematics. A coordinate system. So usually up is the positive direction and down is considered negative, okay? Next, Newton's second law, okay? So Newton's second law says net force equals ma. That is Newton's second law, right? So this whole net force business, we talked about this, right? This is the sum of the forces acting on some object. It's the vector sum. All right, so all the forces here, well, there's tension and there's mg. So those two are going to make up the net force. Furthermore, T is in the positive direction, so I'm going to write one of those forces is T. The other force is gravity in the negative direction, so I'm going to write minus mg equals ma. And so then how is T related to mg? Well, I know, you know already they're the same. However, again, it's important. We're going to start simple and then later things will get more complicated. So keep in mind way over here, the acceleration of this object is 0. Right? That is the same A over here. It's not going anywhere. And even if it was going somewhere, if it was moving with constant velocity, the acceleration would still be 0. So if A is 0, then that means this whole side over here is also 0. Which brings us to the amazing conclusion that T is mg. And we had already solved for that mg. It was 20 newtons. All right, so there you go. The tension in that string is 20 newtons. Now, let's make the problem just slightly more interesting. Okay, so here we are. So for problem number 2, same block, same string, okay? But this time, the block is being accelerated upwards. At, who knows? Let's say it's accelerating at a rate of 4 meters per second squared, okay? And then the question is, now what's the tension? Okay? Ooh, there's a Christmas song playing. It's Wonderful Winterland. So, free body diagram. T, it's the same free body diagram as before, almost. The other thing about these free body diagrams is usually you should try to draw these vectors proportional to their magnitudes, right? So in the previous problem, I know the tension was the same as the weight, so that little up arrow would be the same length as the bottom arrow. In this situation, these two forces are not the same. They've got to be different. In fact, which one has to be greater? If you said T, then you're correct. Which means technically I should draw the T arrow a little bit longer than mg. In any case, coordinate system. So how about we keep the same one we were using? So up is positive, down is negative. Now I'm going to write good old Newton's second law. Net force is ma. So the left side of this equation is going to look the same as it did previously. Right? So there's T acting up, mg is acting down. The difference now is that A is not 0, right? It's accelerating up at 4 meters per second squared. So the term on the right here is not 0, so you can't cross it out. Oh my, what do we do then? Algebra. If T minus mg is equal to ma, then T is equal to ma plus mg. And there you go. Now let's put in the values for these. So the tension in that string is 2 kilograms times 4 meters per second squared plus 2 kilograms times 10 meters per second squared. Okay, math time here. So 2 times 4 is 8. And a kilogram meter per second squared is also called a Newton. Plus 2 times 10 is 20. So that upward tension is now 8 plus 20, 28 newtons. Oh, now she's singing about Frosty the Snowman. 28 newtons. So yeah, if it's accelerating up, there needs to be a net force in the upward direction. That means T has got to be larger than mg. Okay, let's try another variation of this problem. So another variation of this problem, let's do the following. So that would be, so what tension will give the block an acceleration of, who knows, 5 meters per second squared. Okay? So what tension will give the block an upward acceleration of 5 meters per second squared? So, picture. T, mg, coordinate system. Newton's second law. And I am now going to be solving, hold on a second. Oh, this is the same problem we just did. I just changed the numbers around. That's okay. Yeah. Okay. I'm confusing myself sometimes. That's okay. We'll go ahead and yeah. So then T is equal to ma plus mg, because practice makes perfect. So 2 times 5 plus 2 times 10 so 10 newtons plus 20 newtons is 30 newtons. This is the problem I actually meant to do, okay? I think. All right, here's the problem. Let's see. Same block. This time I have a little scale attached here. that shows me what the tension is. So let's say that I'm pulling this thing and this scale shows that the tension is 20 newtons. Okay, so now the question is, what is the acceleration of the block? All right. So this is number 4. Okay, so this time we're given tension, we want to find A. So free body diagram, so there's tension and there is mg. Same coordinate system. And then write out Newton's second law. So net force equals ma. Okay, so then that's going to be T minus mg equals ma. The difference now is I'm, again, trying to figure out what is the value of A. So how about we divide both sides by m? So then on the right, we just have A. Okay, and then so that means that A, I'll rewrite it over here, is T minus mg over m. There you go. Easy peasy, lemon squeezy. So let's plug in the values now. So that acceleration is 20 newtons. Wait a second. No, let's go ahead and do this problem. Minus 20 newtons. I am so silly. Divided by the mass of this thing, which is 2 kilograms. Oh my God. Yeah, 20 minus 20 is 0. So the acceleration is 0. Yikes, why is the acceleration 0? Well, duh, it's because that force is equal to the weight of the block, dummy. So it's not going to accelerate anywhere, okay? Yeah, clearly that force is going to have to be larger than 20. Oh boy, I should just give up now, okay? But I'm not going to. I'm going to do one more. Number 5. Okay. Really, this time it'll be unexpected, I think. All right, let's see if I can do this without totally messing this thing up. So let's say that T is 30 newtons. Why not? Okay, 30 newtons. Good. And now the weight of this thing is still here. The mass is still 2 kilograms. So we're still looking for acceleration. Hopefully it's not going to come out to be 0 here. That mg is 20 newtons. So the coordinate system, again, is the same one we've been using. So now net force is equal to m times A. The net force is still T minus mg. I'm still trying to solve for A. All right, so what's going to happen here? Let's see. So T is 30 newtons minus 20 newtons, that's mg, divided by 2 kilograms. So 30 minus 20 is 10 newtons, divided by 2 kilograms. So now it's going to be accelerating up at a rate of 5 meters per second squared. So there you go. These are just a few simple examples of how to use Newton's second law when you're solving some problems involving blocks and strings. So there you go. Thank you very much.